Hi, and welcome to E3, Conservation of Energy. This is our first conservation law that we've talked about in Physics 11, so it's pretty exciting. You guys should have experienced this and kind of understand it intuitively on kind of your day-to-day life type of scenario. For example, if we're talking about general conservation laws, we can talk about if you had a glass of water. And let's say, for example, that in this glass of water there is 500 milliliters. You could take this water and you could put it into, if you wanted to, you could put it into one cup with 300 mils. And intuitively, you should be able to tell me that if I put the rest of it in another cup, how much is there going to be? Well, if there's 500 mils to start with and there's 300 mils in one cup, and 200 mils in the other cup then, because there's still 500 mils. You could also take it and you could stick 50 mils in one cup. And then in the other cup, you would be left with 450 mils. And this is how conservation laws work. I think we might have to introduce a couple of symbols. No, we don't have to introduce a symbol. We've already seen this one. If we wanted to talk about this scenario, how we could write this is the sum of the volumes at one time is going to be equal to the sum of the volumes at another time. So this little thing up here, this is called a prime, and all it means is at another time. So it's how we can differentiate between this, which is our start, and this, which is another time. It doesn't necessarily have to be the end, just another time. So conservation of energy, conservation of energy is written like this. Sigma, which means to add up all of the energy at one time, is going to be equal to all of the energy at another time. So this is, notice how it's exactly like this. This is exactly like the conservation of volume in our water question. Those volumes stay consistent in all of those scenarios. Conservation of energy is a bit more involved because we have two different types of energy. But you could look at this as saying, at one time, there are two objects. Object 1 has 300 joules of energy. Object 2 has 100 joules of energy at time 1. At time 2, object 1 has 200 joules of energy. How much does object 1 have? So this is a bit of an interesting system. We won't see it again with two objects in Physics 11, but it's just kind of worth thinking about, and we're going to set all of our problems up similarly. So it's worth having a chat. This is assuming that no energy is lost from this system. So we would start all of our questions writing down the law we're going to apply. And in this case, we're writing down the law of conservation of energy, which can be written like this. There's a couple of different ways of writing it down for sure, but this is my favorite. I find it the most consistent with how we approach physics in high school. And we could go, okay, so to start with, this is time 1, and this is going to be time 2. So time 1, I've got object 1's energy and object 2's energy, And at the end, I have object 1's energy and object 2's energies. These are different times. And I'm looking for, oh, sorry, I made a typo up top in the question. How much energy does object 2 have? I'm going to solve for my object 2 in a different time. So I'd end up with an E1 plus E2 minus E1 prime. That's going to be how much energy that second object has. And then we can substitute our known values in. Our 300 plus 100 minus 200. I think I end up with a 400 minus 200 is going to be then E2 is equal to 200 joules. And that's kind of an example of how the equation works. And we can see how, while our original equation looks quite simple, it looks like it's only got two variables, it can quite simply, quite quickly expand into some larger things. Let's look at this next page, which I haven't given a title yet. I'll go back and do that. So let's look at another example. Well, let's talk about mechanical energy. So mechanical energy, which we might see, I think, in the worksheet, mechanical energy is the sum of gravitational potential energy and kinetic energy. Or EP plus EK. And this is usually the simplest way to talk about conservation of energy. So let's look at an example. Example number 1. A skydiver drops 50 meters starting from rest. What is his final velocity? And what you should instinctively do by now is you should look at this question and be like, oh, I can use kinematics to solve this. He accelerates at 9.8 meters per second squared. His initial velocity is 0. His displacement is 50. I want to find what his final velocity is. And 100% you could use kinematics to solve this problem. Not all of these problems you will be able to use kinematics to solve. But it's good to know that for this one you could. And if I don't ask and give you explicit directions to use conservation of energy to solve it, and you're really comfortable with kinematics, that would 100% be a correct and accurate way to go about this. But what I want to, obviously, is I want to talk about this through a conservation of energy lens. So if we imagine our skydiver, and we'll call this time 1, and he starts from rest, and then at time 2, he is 50 meters lower, and now he's got some legs and some arms, and he's going down. His velocity is unknown. So when I set this up, I like to draw my two different pictures. Conservation of energy will always talk about at two different times. We should always have two different pictures. If we set our equation up to start with, we can even put a sigma E on one side and a sigma E prime on the other side. And I now know that my left-hand side of my equation has to do with what I've labeled diagram 1, and my right-hand side of the equation has to do with what I've called diagram 2. To start with, we're only going to worry about mechanical energy. So everything in the worksheet, I think, is just mechanical energy, which is just EK plus EP. And that's going to be equal to EK prime plus EP prime. So if we look at scenario 1, we can tell that he has no kinetic energy. The skydiver is not moving. All of his energy is potential. In step 2, if we decide to define this, which we can do, we can call anywhere we want 0, then he will have no potential energy. Height is quite arbitrary. You can choose to measure your height just about anywhere you want to. So in this case, I'm going to call that 0. And so what I end up with when I simplify this equation is potential energy is going to equal to kinetic energy. This will not always be the case. There are many much more complicated scenarios where EP doesn't turn into all EK. There's a bunch of other things that can happen. But in this particular scenario, I start off with potential energy, and since potential energy is conserved, I then turn it all into kinetic energy. So what you could do is you can imagine you've got 2 cups and there's 500 milliliters of water in one cup. How much of it ends up in the other cup? Well, you pour it all over. So I can then substitute my equations in. Potential energy is mgh, and that's going to equal to a half mv squared. Something should happen. You should notice something's going on. We've never talked about mass for kinematics, so it shouldn't matter here either. And we'll notice that it exists on the left-hand side of the equation and the right-hand side of the equation, so we can cancel it. And I end up with a GH is equal to a half V squared. I can multiply both sides by 2 and take a square root. And I end up with V is equal to root 2 GH, or V is equal to 2 times 9.8 times 50 square root. You should be able to pull out your calculator, plug your things in. I end up with a square root of 2 times 9.8. Now it's giving me trouble. 2 times 9.8 times 50. And I end up with 31.3 meters per second. And there you go. That is how we can use conservation of energy to look at how fast a skydiver is going. Let's look at the next page. Let's look at a runner. There's 2 N's in runner, is moving at 13 meters per second when they grab onto a rope swing. And swing into the air. How high do they get? How high do they get? So our 2 diagrams. We have diagram 1, somebody running. Their velocity is 13 meters per second. Diagram 2, this running person, and maybe we could draw a rope swing there. This running person has been running. They now grabbed onto the rope swing as they're running, and it has swung up to a given height. Maybe this guy's moving pretty fast. I bet that rope swing's at a bit of a better angle like that. If you haven't done this, I don't know about your childhood, but you should go out and give it a go. Run as fast as you can at a rope swing, grab onto it, see how high up into the air you can get. Sigma E is equal to sigma E prime. We start at the exact same spot every time. This first sentence tells us the approach that we're going to use to solve this problem, so that later you know and I know and whoever else reads your work that you applied an approach that is appropriate, or hopefully appropriate, but maybe not. So again, I always start with EP plus EK is equal to EP prime plus EK prime. Sometimes this will get bigger. We could talk about how work plays into this, or we could talk about how friction plays into this, which we're going to do next, I think. But for now, we'll just leave it as EP plus EK. So if we're running along the ground, we shouldn't have any potential energy. So our potential energy in the first scenario should be 0. We can get rid of that term. And in the second scenario, we are not moving if we're at a maximum height. You're going to pause before you start swinging back down at that maximum height. So if you're not moving, your velocity will be 0, and we're left with all of our kinetic energy we want to turn into gravitational potential energy. That will be our maximum height. So we get a half mv squared is equal to mgh. Again, we notice that there's m's on both sides of the equation, and we can cancel them out. A half v squared is equal to gh. I can divide both sides by g, and I get h is equal to v squared over 2g, which is 13 squared over 2 times 9.8. We can pull out our calculator. 13 squared divided by, open bracket, 2 times 9.8, close the bracket, and I get 8.6 meters. I should write it down to 3 sig figs because that's what I like and that's what I expect, so I'll do the same thing. H is equal to 8.62 meters. If you imagine in the Commonwealth swimming pool what the 10-meter diving board is, you realize that swinging up in the air 8.62 meters is pretty darn high. However, running at 13 meters per second is also pretty darn fast, considering Olympic athletes running 100 meters usually run at about 10 meters per second average. So you have to be moving pretty fast to get that high up in the air. Let's look at example 3. This is a roller coaster example. I love roller coasters. Example 3, let's have our roller coaster go up. Let's have it go down. Let's do a loop-de-loop and then continue out. Let's call this 100 meters going over the first hill, which is super big. And then let's call the top of the loop-de-loop. That looks about like 70 meters. And then let's look at a point. Let's call this point B. Let's do this. No, let's not do point B. Oh no, let's undo that. There we go. Let's look at this point right on the ground. Let's call this point B. Let's call this point A, and you guessed it, we're going to call this point C. At point A, it's much more terrifying the slower the roller coaster goes over that first hill. So at point A, the coaster is moving at, I don't know, 1 meter per second. How fast are they going? At B and C. So I'm going to do these in 2 different colors so that we can see them. What we're going to be comparing is, I know some information about point A, so I want to compare point A. And let's look at point B first. Point B. Sorry, I'm apparently not thinking very clearly. I'm not writing very clearly. There's all sorts of mistakes here. Let's try this again. The energy at point A is going to be equal to all of the energy at point B. So I'm going to write this down again. I like my EP plus EK is going to be equal to EP plus EKB. Notice how I shifted my subscripts just a little bit so I can keep track of them. This is a bit more of a complex problem. If I want to, I could put A's here too. Actually, that makes a ton of sense. And since I'm dealing with 3, having a prime doesn't really make sense. So I've just shifted a little bit. So let's look at the types of energy that are going to happen at A. If it's moving at A, it's got kinetic energy. So I can't get rid of the kinetic energy term. If it's not on the ground, or where I've decided the height is 0, then it's also got potential energy. So I can't get rid of any of the terms on my left-hand side. At point A, you have kinetic energy and you have potential energy. At point B, you are on the ground, so I'm going to have no potential energy. So now I have at the start, at point A, I had potential energy and I had kinetic energy, and then at the bottom of this hill, I have all kinetic energy. So let's look at potential energy at point A is going to be an mgh at point A plus a half mv at A squared, and that's going to be equal to a half mv at B squared. You notice how, again, every term has mass in it, so we can cancel it out. I end up with a gh at A plus a half v at A squared is equal to v at B squared over 2, which is super critical if you're designing a roller coaster, that it's independent of mass. If it wasn't independent of mass, you'd have to have a different approach for every single different group of people that went on it, because every single different group of people would have different masses, and some people would make it around the loop-de-loop, and some people wouldn't, and would inevitably get stuck at B, and then you'd end up with a whole schmozzle of work. But since it's independent of mass, you know that doesn't really matter who gets on there, from the very large to the very small, you're all going to go at about the same velocity. Okay, let's finish solving for the velocity at B. I can multiply both sides by 2 and take the square root. On my right-hand side, that cancels, and I end up with VB is equal to the square root of 2 GHA minus a half VA squared. VB is going to be equal to the square root of 2 times 9.8. The height at A, I think, was 100 meters. Yeah, 100 minus a half times the velocity at A, which I think we're moving slow, so it's a 1 squared. I can pull up my calculator, plug these numbers in. The square root of 2 times 9.8. Oh, and I missed a bracket. I think I can move over. That 2 is multiplied by everything in the bracket. 2 times 9.8 times 100, which means I actually forgot to close my bracket over there. 2 times 9.8 times 100 minus 0.5 times 1. I don't know what that's doing. Squared. Close that bracket. Close the square root. That's equal to 44.26. The velocity at B is equal to 44.26 meters per second. I don't know what that is in kilometers per hour, but I guarantee you are moving. 100-meter high roller coaster is also pretty big. All right, so next, let's look at the sum of the sum of the energies is equal to the sum of the energies. We want to know what's happening at C. So at this point in time, I could arbitrarily choose. I know what the energy is going to be at B. I know what the energies are going to be at A. So I could 100% choose. Since A is numbers that are given, that's usually what I will do. It also means that if you plug numbers in early and know how much total energy there is at A, you can just reuse that number again. I'm using variables, so it might take me an extra couple of seconds, but it's not a big deal. I've got at A, I've got kinetic energy, and I've got potential energy, which means the energy kinetic at C plus energy potential at C. So I look at A, again, we just talked about this during the previous part. I am moving at A, so I have kinetic energy, and I'm not at the ground, so I have potential energy as well. So I can't simplify the left-hand side of my equation much at all. On the right-hand side of my equation, I have kinetic energy because I'm going to be moving. If I wasn't moving, I wouldn't make it all the way around the loop-de-loop, and that's not the point of the roller coaster. And I'm not on the ground. So I've also got potential energy. So this equation right now doesn't actually simplify at all. I'm going to have to move pretty quick or I'm going to run out of batteries. I have a half mva squared plus mgha. That's equal to a half mvc squared plus mgh at c squared. Notice how mass is in every single one of my terms again. This ends up independent of mass. It means that everybody's going to end up going around that loop-de-loop at the same speed, independent of who gets on the roller coaster. Half VA squared plus GH is equal to a half C squared plus GHC. I don't know why that squared's in there. Let's get rid of it. I'm looking for the velocity at C, so I have a half VA squared plus GH minus GHC is equal to a half c squared. I can then multiply by 2, take the square root, and I end up that the velocity at c is going to be equal to 2 times a half BA squared plus GHA minus GHC, and then the square root of that whole thing. I'm going to write down here just so I have some space. Velocity C is equal to 2 times a half. My velocity at A is 1 squared plus GH, sorry, not a G or an H, 9.8 times 100 minus 9.8 times, is it 70? Sure is. 70. And the square root of that whole thing, I can pull out my calculator. If I had more practice with this calculator, it wouldn't take me as long. But let's see if I can do it all in one step. I'm going to take the square root of 2 times, open that bracket, 0.5 times 1 squared plus 9.8 times 100 minus 9.8. I missed a decimal there. 9.8 times 70. Close bracket for close bracket for the square root, and I end up with velocity at c is 24.3 meters per second. Thank you for watching, and I just wanted to remind you guys a couple of keys for success. Number one, you got to do the practice questions. If the things I'm saying make sense, that's phenomenal, but you still have to practice and make some mistakes on your own. That goes along with number two. If you get stuck, ask me questions, get in touch, write me an email, make an appointment, or leave a comment on the YouTube video. And step number three to success is look after yourself. Eat good food, get some exercise every day, and socialize as much as you can right now. I hope you guys are all doing well, and I will talk to you soon.